Good afternoon, ladies and gentlemen. My name is Soheil Nazarian. I'm a professor at the University of Texas at El Paso, and it's a pleasure for me to be here to discuss a project that we conducted for the Texas Department of Transportation to promote the further use of the local materials for roadway base and subbase for the low volume roads. In general, our strategy was to propose, investigate, and recommend realistic methods for determining the appropriate use of local materials on low-volume roads by considering several factors, including the structural integrity, the internal stability, environmental conditions, intended use, and of course, the most important one, the cost-benefit ratio, since the goal is the use for the low volume roads, the cost is an extremely important parameter to consider. The goals of the project were twofold. First, to delineate an out-of-spec material from the low-quality material. I would define these in a second. And if a material was considered out of specifications, we wanted to see whether, when, and how we can use it to still get a quality foundation. And for the low quality materials, we just wanted to see if we can add a small amount of additives and turn it to a viable material to behave like a high quality material. Let me first define the difference between an out of specification material versus a low quality material. To do that, I'm showing you an example of a specification I extracted from Texas Department of Transportation, but this same type of specification is very common. There are two components in this one. One, there are essentially the limits for some index properties given the gradation plasticity, and the second part has to do with some engineering testing like the strength test, as you see over here. What I refer to as out of specification are these index test results, that the limits are set based on the consensus and based on the experience, as opposed to the engineering values that were obtained from the parts that are shown in the green. The options we used for using out of specification materials are shown below. The first one was using a thicker layer of local base. The second one was to use the same thickness of the local base, but thicken the hot mix asphalt that we eliminated because of the cost. Improve the stiffness of the subgrade or use chemical treatment. And the other group of options were to combine local and holding base. One was to place a local material, then cover it with a thinner layer of high quality base, and then the other one was mixing the low quality material with the limited amount of high quality imported material to improve the properties. For the low quality materials, we primarily consider to use chemical treatment. I use treatment differently than stabilization. Treatment, we are talking about 1 or 2% of the additives being lime or cement. And depending on the liquid limit and the plastic limit of the material, we would decide what type of stabilizer to use. Some of the consideration were practicality, how economical the solution is compared to the holding materials that are high quality, how implementable and constructible the solutions are. There were some engineering consideration as well. Cause of the material being considered out of specification or low quality was important. Strength property of the materials being strength, modulus, permanent deformation were considered, and the long-term performance in terms of the moisture susceptibility and resiliency were also considered. This is the materials that we considered as an example over here. So we considered one material that is, you see, called Cemex, that it was all green. It means that it was passing all the specifications for a high quality base in Texas. and then a group of other materials from different areas from quarries fairly close to each other, but some of them being considered higher quality than some of them lower quality. And again, you see that the properties, whatever is in red is just failing the specification, and whatever is in yellow is marginally passing or marginally failing the specification. So we have a good mix of different materials that we are considering. Based on the performance parameters, then we started looking at ranking these materials as well. So they are the same materials that I showed you before. Now, instead of the gradation and the plasticity, we started looking at the dielectric constant as a indication of the moisture susceptibility, resilient modulus to get the modulus of the material, permanent deformation, and retained strength. That will be the strength before moisture conditioning and after moisture conditioning, and retain modulus the same way. And the limits are shown over there in the graph. And as you see, in terms of the performance, some of the material are passing, and some of them are not passing the performance. For instance, Turner is basically satisfactory in terms of performance, but it might not be passing all the requirements. But the El Paso one, which is passing all the specifications, you see that it has a low resilient modulus for what we consider a high quality base. So we started looking at chemical treatment for several of the materials and gradation modifications from some other, and of course there were 3 of them that we decided to use as is because they were we considered as to be as high quality. So based on the results that we got, I would just focus over here on the ones that they were low quality, and we started looking at treatment. You see that the first one, that it was not performing in terms of strengths and the classification. Class 1 means that it's high quality. And you see that by adding only 1% cement, we are just basically fulfilling all the requirements, and both in terms of the strength and classification and the plasticity. The same thing for different material. You see that for the second material, the lime was not effective, but the cement was. And all you see common is we are not using more than 1%. And you see that in the majority of the materials, we could engineer with 1% additives to pass all the requirements of the specification and be a grade 1. It means a high quality base. Then we started looking at the performance of these materials now that they were considered grade 1, and we started looking at the values that I discussed to show the performance. And you see that even though we were passing now with 1% cement, we are not fulfilling the permanent deformation. So we're going to get a settlement in the base material if you use it even with 1% cement. So we have to be careful. But what you see, for instance, the Prader over here with 1% cement, we are passing all the requirements, even though we were failing the retain strength and modulus without that 1%. And you see, based on that, again, we can engineer all the materials. And you see, for instance, for the Lubbock Cadell quarry, 1% lime works better than 1% cement because of the high plasticity of the material. Example of gradation modifications, we started just basically removing fines from the materials because of the relaxed values that we had. We found that the gradation needs to be modified significantly more. The change in the gradation by removing fines was only marginally successful. The next step was to just, before putting it into the field, is to test it and make sure that the material is working. So we made these 1 meter specimens, scale specimens, putting it under an MTS dynamic loading system, and we started applying loads on them. And we used seismic testing and dynamic compenetration to get the strength and the modulus of the layer, and then we performed plate load test under the MTS. And this is some of the information that you see. We tested each specimen in 3 conditions: when the subgrade and base were placed at the optimum, and when they were subgrade was saturated, and when the base and the subgrade was saturated. And you see that, for instance, by adding 1% lime, we can significantly improve the performance of the material for this Cadell pit. And the same thing you would see, we can improve significantly with 1% cement the Abilene material, as you see over here. The next step to consider was looking at the structural design. So we decided to see how we can start controlling the rotting and the cracking of the material. Traditionally, the cracking has to do with the tensile strength at the bottom of the asphalt, and rotting was the compressive strength at the top of the subgrade to make sure that the subgrade is not rotting. We were also interested in the rotting of the base. So basically, we started to use permanent deformation properties and a VSYS program to look at the permanent deformation of different layers. One thing that we learned very quickly is an unintended consequences of using thicker, lower quality base, because if you use empirical designs like the AASHTO 1998, is that if you make the base thicker, you're going to control the rotting. And what I'm showing you over here is the same pavement structure, one with a high quality base and the other one with a low quality base. And we are looking at the variation of the rotting with the thickness of the base. And I'm looking from 4 inches of base to 20 inches of base. One thing that I have in mind when I'm using the high quality base, the maximum rotting I'm showing is 1/10 of an inch. When I'm talking about the low quality, I'm talking about 2.5 inches of total rotting. One thing that you would see for the high quality base, as you increase the thickness, the total rotting decreases, as you see over here. Because what's going to happen as you increase the cover, thicker bases, you increase the rotting insignificantly in the base, but you significantly decrease the settlement, the rotting in the subgrade. But when you look at the thick, low quality base, as you see, as we make the base thicker, you're increasing substantially the rotting of the base layer, even though you significantly decrease the rotting of the subgrade. So you should be careful that thicker base is not the solution. So what we found at the top 8 to 10 inches of the base dictates the performance in rotting of the secondary roads. The last item is a cost analysis, and just we're trying to be economical. So there is a critical distance of hauling, and to do that we put a worksheet together to consider the 2 designs for the equivalent number of traffic, one with the high quality, one with the local material, and basically considering the cost of the material and the transportation and break-even point. For instance, in this example you see over here, up to at around close to 50 miles, the cost would be 0, and if it's less than 50 miles, you're better off bringing the high quality material than using the local materials, because the local base is significantly worse than the high quality. so we can do the assessment further. Based on the lessons learned and the information I provided you over here partially, we developed a guideline that I can give you the highlights in terms of the conclusion over here. The first one is, of course, obvious. Depending on the transportation and construction and material costs, the use of local base material can bring considerable cost savings to the project. Especially if you can bring in a competitive environment by having several quarries in the vicinity competing on the cost. Use of small amount, 1 or 2% of calcium-based additives, either cement or lime, may significantly improve the strength and modulus of low-quality base materials. And the goal here is not to stabilize the material, but to improve it so that it will be comparable to a high-quality granule unbound base. Modification of gradation doesn't seem to bring drastic change to the properties of low-quality base material, but it can do some improvements to the other specification materials. The main mode of failure for the secondary roads is rutting, of course, and the quality of the top 8 to 10 inches of the base controls the performance of this rutting. So it's imperative to have high quality or improved material in the top 8 to 10 inches. For high quality or treated base materials, increase in the base thickness will reduce the rutting of the pavement, as we always consider in the design. But for low quality untreated base, increasing the base thickness will basically transfers and promotes the rutting of the base layer. With that, I wish I were there to answer all the questions that you might have. Please feel free to contact me at any time. I'll be more than glad to share the information and our experience with you. I wish you a wonderful conference, and hopefully I'll see you guys soon all in India. And thank you, the organizing committee, for inviting me to be part of this one. Have a wonderful conference. Bye.